Hey everyone, welcome to Maxwell's talk on Parser Combinators. Max is a computer science graduate from UQ, a past secretary of UKCS, and now a software engineer at Google. Um, so everyone give him a warm welcome. Max, you may take it away now.
Cool. Hopefully everyone can hear me. Hopefully someone says something in chat that they can hear me. I'm going to assume otherwise. Okay, cool. Ready to go. About me, this is like me on a slide. If there's like one kind of key takeaway from this slide, it's that I kind of did, 3 years of industrial functional programming. And from that, I've kind of seen what goes right with functional programming, what goes wrong, what's kind of mediocre, what's kind of not worth it. And in some ways, those kind of opinions and that kind of experience is going to come out in this talk. So let's begin. Parser Combinators. Now, before I start the talk properly, I just wanted to give like a few disclaimers. Firstly, like this is going to be a tricky subject matter, and there's going to be times where I might lose people if I make too many logical leaps. Now, normally I'd look at people's faces in the audience to like see how people are going and judge people's facial expressions, but I can't really do that. So you'll need to speak up in chat and tell me to slow down. So secondly, this is going to be like a long talk. It's going to be at least an hour, if not more. So we're going to break halfway for a bit of Q&A, and then we'll kind of push on. And the final disclaimer is there's going to be times where you'll see things that you might be like asking, like, what is the point of all of this? All the pieces to the puzzle kind of fall into place in the last 10 minutes. So if at any time you're like, I don't know what's going on here, and you have to like leave halfway through, my kind of request is like, try and finish it. And I think things will start to make sense if you see that last 10 minutes. So let's begin. Who's had to do this at some point in time? I'd ask everyone to put their hands up, but I can't really see you. But I assume that someone might have dealt with this at some point. And if you looked at the kind of first answer on Stack Overflow, you'd be greeted by something that looks like this. Or this, or this, or this. And so like the first thing we notice about these things is that like they're really, really hard to read. And it's hard to figure out how these work. And if you have to modify these in any sort of way, God help you. But it also kind of like raises an important question. Like, what are these things? Like, they look like line noise. Why do they kind of like look the way they do? Now, the cool part about regexes is they actually map really well to a concept that I think most people would be in some way familiar with. Now, if we kind of consult the sacred texts, the Dragon Book, or this like really great post by Russ Cox. So for those who don't know, Russ is like the current lead dev for Golang. We'll learn that regexes are kind of this textual representation of finite automata. So what does that like mean? It means that like a regex that looks like this, let everyone look at that for a second, turns into something that looks like this. A non-deterministic finite state automaton. And we kind of like look at what's going on. You can see that when we're passing a string, we're saying we want to pass A or B 0 or more times. So we can go up, 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 up on that first node, and then we can transition A, B, B, and then finally to this double ringed third state, which we call the accepting state. So this is like the actual formal definition that might be a better explanation of what I just showed you. And I'll let everyone like kind of read that for a second. So does anyone have any questions about this definition? So like, yeah, the core part is that they are recognized as and there's two different forms of them, and they recognize strings. You know, they take strings and they say, yes, that is what I expected it to look like, or no, this does not look like the form I expected it to. So another thing is, like, you might have expected me to come into this talk to like trash regexes and say like, oh, you know, these parser combinator things are far better. But in fact, like, Regexes is like super cool. And I'm actually going to spend a substantial amount of this talk talking about how they work and why they can be optimized to be like super quick. This kind of sums up how I feel about regexes. So if we like go back to this regex, you can see that we can more or less directly translate this regex into a simplified non-deterministic finite state automata. And if we see what happens when we try and match the string BA, BB, you'll see down here we've got this dot. And this dot kind of represents the read head of the regex. And so when we move that head along, we see that we transition from 0 to 0 on the B edge. And then we are now in two states at once. That's kind of weird because we don't really expect regexes to be, NFAs to be in, we don't really expect automatons to be in two states at once, but in non-deterministic finite state automatons, we can be in two states at once. And so what we've done is we've transitioned on 0 to 0 on the A node, and we've transitioned from 0 to 0, from 0 to 1 also on the A edge. And so let's feed in another A. Exactly the same thing happens. We transition from 0 to 0 via A, and we transition from 0 to 1 also via A. When we put in a B, we transition from 0 to 0 via B and 1 to 2 via B. And then finally, we transition from 2 to 3 via B to the accepting state, which is the third node. And so we can say that this non-deterministic finite state automaton parses B, A, B, B. And so getting to that accepting state, that third and final node, is saying, is the NFA saying, yes, I recognize this string, and we say that the NFA has parsed the string, while noting that the term parser can kind of be a little overloaded. Did anyone have questions there? There was a lot to take in. Okay, seeing no questions in chat. Let's keep going. I'm waiting for people to type things. Instead of multiple states, should it be 1A to 0? No. So there's no way to get. Oh, sweet. I didn't know that, Tom. Sorry. Yeah, there's no way to get from 1 to 0. That this kind of, we're stuck in this state because we haven't, when we're in this state, we don't move from 0 to 1 at any point in time because we're only passing Bs. Does that kind of, I'm going to assume that I've answered that question because of the 20-second delay. So I'm going to charge on. Okay, so let's look at this regex again. So what we just saw was a simplified version of an NFA. It's not really the NFA we construct when we convert a regex into an NFA. So this one is going to be a little more complex. And we're going to construct it using an algorithm called Thompsons Construction algorithm. Now, the really cool part of this algorithm is that there's like a few relatively straightforward rules that kind of power the core of it. And if we run that regex, if we use Thompson's construction algorithm on that regex we showed you before, we would get something that looked like this. I want everyone to like look at the little e's briefly. I'm going to explain what these are in a second. But you can kind of see this roughly the same form as we saw before. You can kind of see that, yeah, we'll get to that in a second. The kind of interesting part is that ABB is shared in both the simplified version and the more complex version that I'm showing you right now. So if we go back to looking at our regex, we can convert it using a series of rules. So this rule says, if I have an empty regex, like if I type grep and just the empty string, we construct an NFA that looks like this. What it's going to do is it's going to pass the empty string. An empty regex will match everything because we can move immediately from I to the accepting state F because we can pass an empty string at any point in time. It doesn't really do anything. If we have a regex that has a single character, that could be any sort of character, whatever you want, we construct an NFA. Sorry, I'll start again. If we have a regex that contains the character little a, we construct an NFA that transitions on a and then accepts. And we would say that this NFA attempts to pass an a. And just re-clarifying, this is an NFA that passes the empty string. So if we have a regex that has like multiple parts, where each part is represented by either an S, or these two parts are represented by S and T, we kind of glue the NFAs that correspond to these subparts, which we've called NS and NT, and we glue them end to end. If we have a regex that has multiple parts separated by a pipe operator, we kind of permit transitioning to the subpart NFAs NS and NT via empty string transitions, and then back again to the accepting state. And so what this kind of allows us to do is to create an NFA that attempts to pass two things at once. If we're remembering the fact that NFAs allow us to be in multiple states at once. So when we get to this construction, we will transition on both empty strings to start passing both at once. We're going to see how that works in a second, but I just wanted to describe this particular part of the construction. The next one is S+. So S+ says that, wait, my notes are wrong. Yeah, so if we have a plus after any part of the regex, we construct an NFA that attempts to pass with the NFA constructed by S one or more times. So what we do is we pass the empty string. We have to pass using S at least once, and then we can pass the empty string to get to the accepting state. But if we have star, what we can do is we can skip the NFA that corresponds to S in the middle. So we will pass S 0 or more times because we can just skip over the middle one and go straight to the end. Also noting that this, what would I call, this empty string edge allows us to pass NS multiple times. So in practice, let's go back to our regex that we looked at before, and we're going to reconstruct the complex NFA again, and remembering that those rules that we were looking at before. So you can kind of see those parts. We see that this section is created by the pipe operator. You know, if my mouse is not turning up the 2, 3, 4, 5, 1, 6 section, we see the 0 and 7 nodes are created by the star operator, and we've joined the ABB section to the initial bracketed section by bolting those two parts of the NFA end to end. And so let's try and pass the string. Oh, we got a dab, hell yeah. Let's try and pass an empty string. So remembering, in this initial state, we can pass the empty string at any point in time. So I'm going to give a simplified version where I'm only going to indicate a bunch of states that we really care about. There's actually more states that we're in at any point in time when I'm showing this diagram, but I'm only kind of showing the ones that we kind of give a shit about. So let's pass all the empty strings. And so you will notice that I was able to get to these states via edges that have the empty string. So we can be in 2, 3, 4, 2, 4, and 7. Let's feed in our first B. and we transition from 4 to 5. You'll note that I'm actually in state 4 because I can transition on the empty edge from 5 to 6 to 1 and then back to 4 again. But I haven't indicated that. So don't get any like impressions. This is a simplified version of an NFA parsing algorithm. So let's parse another B. Yep, we looped. We went from 5 to 6 to 1 to 4 and back to 5 again. Let's parse an A. We see that we have 2 shifts at once. We've moved from 2 to 3, and we've moved from 7 to 8 via the A edge. Let's parse another B. We transition on a B edge from 8 to 9, and we transition from 5 to 6 to 1 to 4 to 5 via empty, 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 empty B. And then finally, our final B moves us into the accepting state via 9 to 10, via the B edge, and you know, we've passed the string. Congratulations, awesome. Oh. So we still have a problem. From an algorithmic complexity point of view, like handling multiple states and multiple transitions at the same time, it's not great, you know. There's the great part is there's like another algorithm called the Parser Construction algorithm. Now the really cool part, I'm just gonna like give you the Wikipedia excerpt. You'll see it says something about like converting a non-deterministic finite state automaton into a deterministic finite state automaton. Why is that cool? We only have to care about one state because finite state or DFAs, deterministic variants, are only in one state at any point in time, which is great, kind of cool, you know? And there's another algorithm called DFA minimization that we can take that DFA that we've just produced using the Parser construction algorithm, and we can like squish it down. We can get rid of all these like extra states that we don't really like care about or just are kind of like redundant, and we can like merge them and compress them in a kind of way. So from a regex, we can go from the construction algorithm through the Parser construction algorithm, and then finally through the DFA minimization algorithm to produce this like really compressed, efficient, you know, automaton. Now, if you've used Python and like the regex like module, you know, the regex standard library in Python, you've noticed that you have to like compile your regexes. Those 3 previous steps I just described are kind of what's happening. The specifics might be a little different, but you know, there might be languages that actually do those exact 3 steps I just described. So yeah, that's what like regex compilation is doing under the hood. Yeah, cool. So if we look at that NFA that we had before, and we run those 3 algorithms, we get something that looks like this. You can see it has a lot more, less states. We only have to care about one state at once. And yeah, it's really kind of nice, memory efficient. It's probably really fast. Yeah, pretty cool in my opinion. So if you like squint really, really hard, I might be like barking up the tree a bit right now. You'll notice something kind of cool. So let's just like pass in some characters. What you'll see that the transition from 0 to 1 just then was handling both the A or B star section and the ABB part of the regex. That the DFA minimization has caused the DFA to almost reuse parts of the parsing infrastructure to cover different parts of the regex. That's awesome. I'm sorry. That's dope. So yep, for completeness sake, I'll finish parsing that regex. So this is the DFA that passes that string. Cool. So yeah, like few key takeaways. Regexes can be converted to non-deterministic finite state automatons, and that they have finite states. We have a rule-based mechanism for this conversion process. where these rules combine NFAs together to form larger NFAs. Particular stress on combine, and we're going to get back to that in a second. Yeah, questions. I would love questions. That was a lot of content. And also another thing is this, like, you normally take a lot longer to learn this if you were to do it at a uni course. We do it, I think it's Comp 403 has a section on these kind of algorithms in a lot more depth. You actually cover how Parser construction algorithm is actually implemented. Kind of a nice algorithm to do on paper. Oh yeah, combine, yeah, funny that. Okay, let's power on. I've got no kind of questions, so let's begin. Okay, I just need a drink, sorry. So this regex at the top of the screen, yeah, it's in compilers and interpreters, yeah. It will pass the following 3 strings. What if we wanted to pass these 3 strings? Can anyone suggest to me a regex that compiles to some finite state automaton that could pass these following strings? I'm thinking, and I can't really think of a finite state automaton that would pass something that looks like this. And the reasons why are, like, say it like passes like 3 A's, how would it know to remember to pass 3 B's that immediately followed that? It would almost have to, like, remember some sort of, like, arbitrary number of states in order to pass the second part. You'd have to, like, remember how many it passed in the first part and then pass exactly the same number in the second part. It's almost like you need some sort of infinite state, finite state automaton, or infinite state automaton. It's kind of not what a regex is. It's kind of an issue. Now, if you've spent some time on Stack Overflow, you might have come across this great thread. It seems like a pretty straightforward question, right? And you get this answer. It's a bit long, but I'm going to let people get to the end. It's pretty funny. So you'll notice the kind of final line, which is, have you tried using an XML parser instead? So this kind of begs the question is, what is the difference between a regex and a parser that we're kind of using common parlance? You know, before we were talking about how regexes parse things, but would we call regexes a parser? Yeah, maybe. In this kind of situation, the commenter has reserved the word parser to just describe an XML parser, something that seems infinitely more complex than a regex. So what's so special about parsers, quote unquote, that regexes can't do? And this is another answer to that exact question on Stack Overflow. And you'll see the commenter has said that, well, HTML is a type 2 context-free grammar, but regexes can only pass type 3 grammars, which are kind of aptly named regular grammars. The reg in regex meaning regular. And if we go to Wikipedia and look at the Chomsky hierarchy, we see that type 3 finite state automaton, like type 3 regular language, is passed by a finite state automaton, aka the thing we've just been talking about for the past 30 minutes. And you'll see that L is the language, is the set of strings of repeated A's of any length, where a language is a thing that an automaton can match. Now, if you have a look at the example for the type 2 context-free language, you see that it's a set of all strings with a repeated number of A's followed by an equal number of repeated B's, which happens to be the strings we were looking at in this slide. That matches the form of these strings. So we can conclude that these strings, based on that table we just looked at, form a type 2 grammar. And so we notice here that a finite state automaton, given that it is in the final row, cannot parse a type 2 grammar. That a type 2 grammar is strictly too complex for it to comprehend. And Wikipedia here is telling me that I need some sort of non-deterministic push-down automaton. We need some sort of parser of some description, something a little bit more powerful. I'm not going to show you a non-deterministic push-down automata. I'm going to show you something different. Let's write some code. So, first of all, a few disclaimers. Is that font too small? Can I make this bigger? Okay. Wait, I'm not presenting this in a lecture theatre. I just realised. This font can be as small as possible. So first of all, it's in Scala. I'm really, really sorry. I would have rewritten this in TypeScript just to make it easier for people to kind of understand and work and play around with. I just frankly did not have time. Because this is a language that a lot of you have not used, slightly bigger. Okay, let's go font size. Font size. 19. There we go. Okay. Oh yeah. Cool. Because this is a language that a lot of you have never dealt with, like absolutely 100% feel free to ask at any point in time, what the fuck is that syntax? Another thing is, when in doubt, here's like a little razor that I can kind of suggest. Pretend it's statically typed Python, and you'll kind of roughly get Scala-ish semantics if you're like confused by the syntax at any point in time. So let's build, what is that syntax? Yeah. Okay, let's build a parse combinator. Let's begin. So first of all, a parser. What is a parser? So a parser is a wrapper around this function that takes some string, where that string is the input stream of characters that we're feeding into the parser. And it can respond with two things. It can either say, no, I did not pass anything. It can optionally say, no, I didn't pass it. Go away. Or it can return a tuple of some type A, where A is the result of the parser, and the rest of the input stream with the read head moved forward one character. Now that's a bit confusing, but let's go to the item parser, which is the canonical, most primitive parser that we can possibly construct. And so here is that most primitive parser. And so here we have a parser, and what it's going to do is it's going to create a function that, so this parser wraps itself around a function, and it looks at that input stream, and it says, if the input stream is empty, there's nothing in it, it says, I could not pass anything. No, none, nothing to pass. If it gets an input stream, which is a string, what it will say is it will get the first character of that input stream, and it will give the rest of the, and give us back the rest of the input stream. And so this is a parser of a single character, a char. It's a parser of char. And so here's it in use. If we say parser, item, parse, and we cram in this A or B, so we pass in this string AB, what it will do is it will pass the character A and the rest of the inputs, and then it will give us back the rest of the input stream. And so in other terms, it moves that dot that we were looking at before in all those regex demos along one. You know, it's moving this dot AB to an A dot B. Any questions? This is like the rest of the entire talk is kind of contingent on people understanding what just happened there. In fact, I might quickly do some live coding to simplify this a bit, because that is a syntactic kind of shortcut. No, that's not going to work. Oh, ta-da! Let's go back to what it was. Okay, cool. We've got no one asking questions, so we're going to proceed. So here's another primitive operation. Here we're constructing a parser that takes. We have a function that takes a value and it constructs a parser. Yeah, match is meant to be pattern matching. So we've elided the actual match, the match keyword. It's kind of a weird Scala shorthand that I shouldn't have done because a lot of you aren't familiar with this. Sorry about that. But yeah, this parser is inspecting whether the input stream is either empty or non-empty. So yeah, back to this unit function. So this unit function, it's going to take a single value and it's going to construct a parser that looks at the input stream and just doesn't really do anything with it. It just spits it out the other side. And it parses that single value. So here we have a parser. What it will do, parser unit true. And then when we give it AB, it just says, I pass true. We've kind of forged a parser. It didn't really pass true at all. In fact, it did nothing at all to the input stream. As you can see, the input stream is completely unchanged on the other side, but the value that is returned is true. And then on the other hand, we have another function called failure. And failure just constructs a parser of any type that takes the input stream and just gives up. It says, I didn't pass anything. None. Here you go. You have no value. You're not getting anything out of this parser. This is in some ways equivalent to a regex of infinite length that just, it's impossible to provide enough to that regex for it to pass something. Cool. And so what we can see is we have this run function that what it will do is it takes an input stream and it goes to the parse function and it inspects the answer. And so ideally what we want is we want to consume the entire input stream. And if we get a result, we say, well, this is the result. If we have an input stream that is not entirely consumed, as in it's not the empty string, we say, well, we didn't consume the entire stream. And if we get a none, as in we weren't able to pass it, we say we give up, pass error. Sweet, cool. So if we scroll back up, so we're remembering that parser is a wraparound of function from string to this optional tuple. We can kind of transform parsers with a map function. So what we can do is we can take some sort of parser and some function from A to B, and we spit out some parser of B. And so how do we do this? We construct a brand new parser that wraps itself around this current parser that we're in the context of. This is just a class and this is just a method definition. And we say, we look at the result of the parser. And if the parser has been like, here's my value, I've offered up some sort of A and some sort of result stream, we map over, we transform that value with this function, and we return the rest of the string. If that parser had failed, this parser also fails. So as an example, here we have parser. This parser, what it's going to do is it's going to pass the first character, because we're using the, oh, wait, no, I've written this wrong. There we go. Much better. Much better. That's correct code now. So this parser item, and then what we do is we map over it, and then we pass in the input stream. And what it's going to do is it's going to get the first character out, because this is a parser of the first character. And then it's going to convert that character to its integer representation in ASCII, in that case 97. And it leaves the rest of the stream completely unchanged. Did that make sense? Because we're going to get to some more complex examples. Okay, seeing no questions. I have, cool. So this is kind of another complex one, which is a flat map operation for our parser. Now, let's just like read the commentary that I've kind of like read. So like a flat map operation for a parser type will take one parse operation and it will compose a parser function over the result of the first. So here's like that thing I showed you before is like parse ASCII code. This is a parser of int. Because it takes the first character, it parses the first character and then converts it to an int. And then what we can say is we can reuse this parser twice. We can say parser, and we have a function that takes the result of the first parse code, and then we do another parse, and then we take the result of that second parser. And then what we do is we add them together. Oh my God, I have not updated these docs. And then what we do is we add the result of the first parser to the result of the second parser. So if we like in chat, if the latency isn't too long, what's going to replace this triple question mark? Given that this passes an initial ASCII code of the first character, this passes another ASCII code of the second character, we've passed in A and B, remembering that the ASCII code of A is 97. Can someone do some quick math for me for this one? Okay, the latency is really long on this stream. Okay, cool. The answer is 195. It's 195. And that's because it's 97 plus 98. And that's the result of this parser. So this parser overall is a parser of int. It's a different type. It's not parsing a string anymore. Because we've flat mapped over it, we've converted, because we've mapped over it initially, we've converted it from parsing characters to parsing ints. Okay. Now, what you'll see is this did one parser after the other. We passed an ASCII code, we passed the first character, and we passed an ASCII code again, we passed the second character, we passed A, and then B. Now, Scala in its infinite wisdom has provided special kind of syntax for me that will convert these flat maps. If I wanted to repeat this operation, I don't know, 7 times, what we would see is almost like kind of pyramid of doom. We would have these nested flat maps within nested flat maps within nested flat maps within nested flat maps. And that it's kind of ugly code. And so what we have is we have a special notation called for notation. And what for notation is going to do is it's going to build up these flat maps for us. And so you can kind of see there is a direct desugaring from this code here to this code here. So whenever you see me using this kind of for notation, you want to think of me taking a parser and using the results of previous parsers to make new parsers. And we get bigger and bigger and bigger and bigger parsers using this flat map operator. And so if we actually to look at the implementation of how this flat map function kind of works, is that it's going to create a brand new parser. It's going to create a brand new parser that takes an input stream, feeds that input stream into the current parser that we're trying to transform. And we take its resultant value and its stream, we convert its resultant value with this f to produce a brand new parser. And then we push in the stream from the previous parser into this parser. Now, that's a lot to understand implementation-wise. I don't really need you to know that, but all I need you to know is that this is a mechanism for us to sequence and run parsers one after the other. Cool. Now, with that, we can start to build tools that are actually going to be useful for us to parse, text, characters, parse, strings of text. So let's look at this satisfy operation. So satisfy operation is kind of cool. So what does the satisfy operation do? What it's going to do is it's going to parse the first character from the input stream. It's going to run some predicate function, and it's going to look at that, and it's going to be like, does that meet the criteria that we've specified for this character? If it is, we say, yep, that's all good. I'm going to return a parser that just returns that value. But if it doesn't, it says, well, actually, what you gave me, I don't like. I didn't satisfy that kind of predicate that I've got up here. I'm going to fail. And that fail is saying, nah, I didn't pass it. Go away. And so here we can build, we can kind of build two kind of tools. Char is a function that will parse, creates a parser that will parse a specific character. So a char of A only parses A. Remember that from our regex, where we had that construction rule that if we have a single character in our regex, we could construct an NFA that only matches that specific character. That char is its equivalent. So what it does is it will only pass if it satisfies if that character is equal to that character that we specified. And so one of is another one that is going to be kind of useful, which is equivalent to if you've ever seen a regex that looks kind of like, A, B, C. Assume that is a regex. This is, oh no, there's no commas in between it. This is a regex that matches A or B or C. And one of takes a list of characters and it will successfully pass those characters if the character that we pull from the head of the input stream is in this list. Cool. So I should have put some documentation explaining how these worked. Let's write them right now. So parser dot one of A, B, let's go list A, B, C, parse C equals sum C empty string. Ta-da! That's how it works. So now that we've kind of looked at those kind of this kind of like core machinery, let's scroll back up again and look at this operator. Now, this operator is, it's pronounced either option or alternative. And what it's going to do is it's going to construct a parser that attempts to feed its input to two separate subparsers and then yield its value. Feed its input to a subparser and then yield its value. But if that parser fails, it goes to the second one. And that's like that's functionally equivalent to this kind of pipe operator that we see in regexes. So what the hell has IntelliJ done here? So as an example, if we have item or failure and we try and parse with A or B, what we'll see, I'm sorry, this is completely mangled, the example that I've kind of given. It's kind of upsetting. Weird. What was that meant to be? Sorry, I've been cursed by the demigods here. This is a bit embarrassing. Ignore that. Ignore that entirely. So let's scroll down to equivalence. Okay, cool. So let's actually see these kind of parsers in action. This is a bunch of code that what it's going to do is it's going to take some sort of regex pattern and it's going to take a parser and it's going to compare how they work for a bunch of inputs. First one is good. Second one should be failure fast. Yeah, that's what it should have been. Yep. Sorry, Tom. And so you don't really know how to understand how this kind of machinery works, but let's actually just like see how it works. So check pipe. What check pipe is going to do is this is our initial regex, and we're saying we want to pass A or B, and this is functionally equivalent to parser char alternative parser jar B. And let's punch it into the code. Check pipe. Ta-da! What the hell? Stack Overflow? What's happened? That's really bad. That's really, really, really bad. Someone should show me, can someone put up like, sorry, we're experiencing technical difficulties? Far out. Okay. Oh no. Oh no. No. Okay. Okay. Everyone take a break, grab a Snickers. I'll be back in 5 minutes. This is really bad. Oh no. I tested this before. Oh. Oh no. No. Okay. Let's see if this works. Okay. I might have ruined the talk if this doesn't work. Okay, so let's try check. Where is it? Equivalence check pipe. Okay, it's working. Okay, I just saw my life flash before my eyes. Sweet, we're in business. Okay. Whoa. Okay, so let's go back to it. Where was I? Fuck. So yeah, check pipe. So we can show that this regex is directly equivalent to this parser. And we're going to go looking at why this works. Check plus. How does check plus work? Check plus. Once again, the first column is the regex saying if it can pass the string that was specified or not, and the second column is the parser. And so what we can see is check plus. This regex that we've specified here is identical to this parser that we've specified here. Let's go check star. We'll see that the star one, where star can pass 0 or more A's, reminder that check plus passes 1 or more A's is equivalent using this very special star method. And then check any of, which is that one I showed you before. If we go check any of, we see that A, B, or C surrounded in square brackets is functionally identical to this one-off parser function that we've specified. So awesome. So how are these things working? First of all, let's look at this pipe operator. Yeah, this pipe operator, what it's doing is it's constructing a parser, takes the input stream, crams the input stream into the first parser that we're wrapping itself around. If that parser says, actually, no, I didn't parse anything, goes to this second parser QA, crams in that string again, and then takes whatever the result of that parser is. Otherwise, if it did successfully pass what it passed, it says, yep, cool, here's the result. Now, here's another part, a special kind of useful, important function that we kind of have to describe. And this is called the app function. Now, what the app function is kind of interesting is it's going to take 2 separate parsers, where one of the parsers hasn't passed a value, Well, it has passed a value, but it's passed a function. And that function, what we do is, if that parser succeeds passing that function, we take that function and we apply it to the result of the next function, of the next parser. That's why it's called app, you know. So yeah, it's kind of super weird, but you can see this kind of like parse ASCII code. What it's going to do is it's going to take, what we do is we map over parse ASCII code to convert it from first initially a parser of int, and we convert it into this at point in time is a parser of int to int. It's a parser of a function. It's kind of cool, but yeah. And then what we do is we apply it to the next parsed ASCII code. And so if this is a parser of int to int, using the result of the first ASCII code, what do you think this is? Well, it's the same thing as the flat map we had before. It's 195. So once again, app is this way of causing parsers to be sequenced in order of each other. You know, we have one parser and then another parser in much the same way that flat map does it. And yeah, you can kind of see this implementation. It says, well, we create a brand new parser. It takes the first parser, crams in the input string. If that succeeds, we get its function. We go to the second parser. We cram in the next input string, which is the one that has had its read head incremented in some sort of way. We get its value out, and then we finally succeed, and we be like, okay, we've successfully applied the first function to the second value. If any of those don't work, we create a parser that doesn't work. So in its actual practical application, what we build is we build this plus operator. And what this plus operator is going to do is it's going to build a parser that is going to run itself over and over again, and it's going to collect its results up into a big list. This is kind of hard to grasp, but just trust me that that's exactly what it does. It's going to repeatedly apply itself until it spits out a list of results. Whenever, you know, until it gives up. It's going to like, oh, I can't pass anymore. Here are the results. Important to note is that this lazy operator right here is like kind of core to how, like why this is written in Scala. This whole talk would be like really painful without this like one word. It's kind of funny. And then star is, remember like how we could skip, like I'll bring back this this graph in where were we, right? Like remember this? Oh no, that's not what we wanted. It's this one. Yeah, there we are. We have to pass at least once with plus, but if we have star, we can like skip it. Well, this is like exactly the same. We can like, if we have a plus, we can just like skip it if it doesn't work. Kind of cool. Yes, those functions are mutually referencing each other. Hilarious, isn't it? Cool. So we kind of see how these like kind of little cool like little operators, these like stars and these pluses can do cool things and are like kind of functionally equivalent to regexes. And now this is like the kind of moment of truth. Remember how I was like talking about like parsers can parse type 2 grammars? If we go like check type 2, bam, here's like the regex like completely unable to parse this type 2 grammar, but the parser's having a great time. It's quite successfully parsing it. And you can kind of see how that type 2 grammar works is that this S, it kind of depends on itself. It's saying an S can be an A, it can be an A or a B, or it can be an A, S, or B. And so that can repeat. And when that repeats, that recursion repeats, it will ensure that there's an equal number of A's on the other side as well as the B's on the other side. So a parser is almost like an almost direct transliteration of the grammar of this type 2 grammar that we've specified that we were unable to previously parse with regexes. And so we're saying we can pass either an A or a B, which is that bit, or we can pass an A or an S or a B. And if we succeed at that, we just like smush all of them, like smush all like the sections that we've passed together. It's kind of cool, you know? So yeah, cool. Type 2 equivalence. Awesome. But you'll kind of notice something, which is this is like the A or B star ABB regex that we kind of did before. And you can kind of see my transliteration of that. We have like A or B star and then ABB. And let's do check type 2. No, sorry, check type 3. I wrote the wrong function. There we are, check type 3. Now you'll see something like kind of weird, is that the parser is now failing to parse these strings. And can anyone like guess why that's the case? Oh, keep forgetting about the latency. So what's happening is this parser it's running up, and because it's passing A or B 0 or more times, what it will do is it will get to this entire string and it will exhaust the entire input stream. And it will fail to pass this A, B, B. It'll just be like, I couldn't do it. So anytime we try and pass these strings, the parser combinator, like it fails. It's like, I can't do it, you know? Which is like kind of annoying. But it turns out we can actually still pass these strings. We just have to change it in a way. And we have to do something like this. So what we've done is we've rewritten the grammar. We're saying that the thing we're trying to pass is either an A and the rest of the stream, or A and the rest of the thing we're trying to pass, a B and the rest of the thing we're trying to pass, or an ABB. And so what this is effectively doing is we've removed left recursion in the grammar that we were originally trying to pass, which, you know, it's kind of annoying, but we're going to talk about like ways of getting around this. But yes, we can still pass this regex, but we've had to modify it in a way. The really cool part is that the grammar that we've had to write in order to correct this is almost directly transliterated from what we've constructed. So we're saying like a G, it's either an A and a G, or it's a B and a G, or it's an ABB. And so we can check that, we can check the equivalence here. As we can see, check type 3, take 2. This is the brand new version. Ta-da, it's working. Awesome. Isn't that great? We've successfully proven that we can pass the same things as a regex. Cool. Okay, so this is like, that was a lot. Unfortunately, there's more. We've still got more content. But that's enough on regex equivalences, and we're going to move on away from the core machinery of the parser combinator, and we're actually going to try and build cool things. So, you know, if you're kind of bored right now, it's going to get really interesting. Okay, let's build some like useful things. Let's build a parser that parses white space. You know, it's going to parse white space. What it's going to do is we're going to say white space can be new lines, it can be carriage returns, it can be empty strings, and it can be those repeated over and over and over again. We can say alphanumeric. We can pass alphanumeric strings by saying that every character must satisfy the isolator or digit function, and what it has to be, and it has to be 0 or more of those. That should be a plus. I don't know why that isn't a plus, but it should be a plus. And we can repeatedly pass it if it's a letter or a digit. we can pass a string by, first of all, passing a character and then attempting to pass the rest of the string, character by character by character. As you can see, like parser alpha pass hunter2, passes hunter2. Awesome. Token, what it's going to do is it's going to take a parser and then it's going to try and pass white space after it. So pass a token of some sort of char character, and if we try and pass a character A with a bunch of white space after it, it's going to extract out the A and it's going to leave the rest of the stream. Like it will munch through all of that, white space. It will get rid of it, chuck it away. Reserved, what it's going to do is, what does reserved do? Oh, yeah, it takes a string. In this case, not a parser anymore, and it wraps it in token. And so you can see a reserved A, it's an A followed by a bunch of white space and A. Digit, passes a digit. Pretty self-explanatory. It has to be a digit. Natural's fun. I like natural. Natural says, we're going to get this parser of digits. And then what we're going to say is, if we have one or more, what we're going to do is we're going to collect all those results, because that's reminder that this plus is oh, come on, Scholar. You see this plus, it's a parser of a list of char. What we're going to do is we're going to collapse all those characters that we've repeatedly passed that are digits, and then we're going to convert all of that into the digit that is equivalent that we've passed. Number, not a natural anymore. What we do is we try and pass a sign, and we pass a sign by either trying to pass a negative sign at the front, or we just try and pass nothing. And then what we try and do is we try and repeatedly pass digits, and then we get a pass repeat. Surrounded is kind of, as you can see, yep, pass -420, we get, oh shit, we get 420. Surrounded, what it's going to do is it's going to take a character, some opening string, it will take a parser and some closing string. And what it's going to do is it's going to attempt to pass the opener, it'll pass the result of the pass we've wrapped ourselves around, and then we'll pass the closer, and then we'll return the result of the thing that we've passed in the middle. Now, now for chain. Chain sucks, because chain's really confusing. And the reason chain is confusing is it kind of does this kind of mutual recursion bullshit. And it's just generally confusing. But the kind of cool part is chain is kind of useful for passing things that are separated by other things. As an example, if we have 1 + 2 + 3, these 1s and 2s and 3s, these digits are separated by this plus operator. In this case, these 1s, 2s, and 3s are separated by a comma operator. So what we can do is this chain function we provided a parser that will pass the digits, and we provided a parser that will pass the commas and the pluses. Or in this case, it's like parser A, this parser A to A to A. And it will spit out some final A. It will pass some final A. And it's using this A to A to A to combine each of these together. In practice, that sounded like gibberish, but if you just look at it being used, it kind of makes sense. So this is we create this parser, this is parser int. It passes the addition operator, and this addition operator we kind of imbue with its behavior. We say that an addition operator, what it will do is it will take 2 ints and it will add them together. And we use this chain L operator, and we say pass a number and use this parser of addition operators, and collect it against 0, the final, it use 0 if we weren't able to pass anything at all. And if we feed in this, this string of 1 + 2 + 3, it's going to spit out 6. It kind of seems like magic, and frankly, it is. The fact that this is even possible is like awesome. Constantly blown away by that fact. But yeah, ignore the fact this is the way we parse things that are separated by characters. Now for a moment of truth. I notice I have hemorrhaged over 15 people from the live stream. We've halved the total number of people who are watching this. Great, I love it. Okay, so reduce, yeah, but it's a parser. Yeah, it's exactly what it is. Hey, let's parse JSON, or at least like some simplified version of JSON. So what I've done is I've gone to the JSON website, and yeah, fuck, yeah, reduce, but it's the audience. And I've just like copied the EBNF grammar, and I've torn out a bunch of the stuff related to how to handle like exponentials and decimals and a bunch of like number related bullshit. But we get the real core of what JSON is. And we can see like JSON, it's like a bunch of elements, and those elements are surrounded by white space. Those elements are values surrounded by white space, where values can be objects or arrays or strings or numbers or the true or false or null, and objects is it's a bunch of key value pairs, and arrays is a bunch of elements separated by commas. You know, you get the gist. We all know what JSON looks like. So like, let's like just try and translate this directly. And this is like, it's cool. I'm going to close this for a second. Oh no. And we're just going to like v-split this. Oh, come on, v-split. Thank you. Okay, cool. First of all, so we create this object, it's JSON. And JSON is built up of like these how many is that? 7 core data types. So 7 core data types, they can be string, they can be numbers, they can be objects, they can be arrays, they can be true, false, or null. And you'll notice that object contains a map of string to JSON. An array contains a list of other JSON. So it kind of depends on itself in a kind of fun little way. Now, if we scroll down a bit, so this is like what we're trying to map our parser onto. We're trying to parse JSON. And so what we do is we define a method called parse. It takes a string, it gets JSON, and then it tries to parse it with that string. And so what is JSON? JSON is an element. JSON is an element. Value is an object, array, string, or number. Value, object, array, string, or number. We're just like copying this directly. Like, it's awesome. This is dope. Big fan of this kind of stuff. Object. Yeah, you know, it's a bunch of pairs surrounded by curly braces. And we write that, pairs surrounded by curly braces. And it's an object. Pairs are, yeah, now this is where chain gets added. So pairs are singular pair of entities separated by commas. And so we say chain L, they're singular pair like elements, and we're merging the result of this pair with empty maps. And where our pair is, it's a bunch of white space, we try and pass the key, we pass a bunch more white space, we try and pass the colon operator to kind of separate it from its value, and then we pass the value. And that gives us a single part of the object that we're trying to pass. It passes almost one line of that part of the JSON. So like, yeah, like that's kind of like, that will like quite successfully like, let's write, oh, what the hell? That's not how you write comments. Let's write some code. If we try and pass JSON pair pass a, it's going to be a key colon 5. What that's going to give us is equal to some map key number J 5. yeah, that looks roughly correct. So yeah, that's kind of, you kind of get the gist of what's going on here. It's passing like a single key value pair. It's kind of really cool. So map merger, what it's going to do is it's going to take the result of these, like passing these key value pairs, and it's going to mush them together. And it's mushing them together anytime it passes this comma operator. So we kind of effectively do the same thing with arrays. We say, well, an array is a bunch of elements surrounded by square brackets, and those elements, they're elements being smushed together as a list. And list, the list smusher thing is whenever we pass a comma operator, we smush the thing we've passed repeatedly together. Element, it's just a value surrounded by a bunch of white space. A string is any kind of alphanumeric string of characters surrounded by quotation marks. A number is just the number pass we defined before, converted to a double. True is just passing the string true, converted to our true JSON value. False is, you're getting the point here, et cetera, et cetera, et cetera. Now, this is a really cool bit. Let's get some JSON. Here's some JSON that we've written, and let's get the JSON parser, and we're going to just cram it in, bam, and this is what we get. So I'm going to close this. That's what it spits out. We get a. Hopefully my console is still open. Let's bring it open to show you that I have not cheated here and that this actually works. JSON parse tree, passed null. I cheated. That did not pass successfully. Anyway, I've broken something between 30 minutes ago and now, but fortunately I saved what it was giving me before, which is awesome. So what you can kind of see is, this string gets passed to this kind of Scala object. And yeah, it's successfully mapped a string onto some structured data that we wanted to produce. Awesome, it's working, woo! And yeah, that's what our pretty formatter was spitting out before. Now, here's a really cool bit. Because this is like structured data that we've successfully passed, it means that we actually get a bunch of type safety guarantees because we've built it in the language in which we actually do the parsing. That's kind of strange to hear. But as an example, if we were to write, some Java, pretend we're writing JavaScript right now, and we try to do this field, we'd be allowed to do that because, well, true is a valid JSON object, JavaScript object, and field that would probably produce undefined. Correct me if I'm wrong. My JavaScript's a bit rusty. Now, here's a really kind of cool part: is that if we were to wanted to look up some sort of key on whatever we've passed, see, this is the JSON that we've passed from before. Oh, wait a second. Oh yeah, that's still no. Anyway, this is the JSON we were trying to look up before. We can't go past get field. I don't know, what field do we want to look up? Object, right? We're not allowed to do that because the JSON object in Scala doesn't support that. There's no kind of method that says a lookup field. Instead, it's one of these 7 classes. Now, if we wanted to write a safe key lookup, key lookup operation, we have to handle every possible case that this JSON can be in. So the really cool part is let's go JSON match exhaustive, and it will say, okay, cool. JSON could be any of these 7 types. And the only thing we can actually look up keys for is objects. So we'll just go members, get key. And then in every other case, we can say, well, in reality, you actually can't look up that key. And so now we have a safe lookup key function. So if we go past and the key was object, if this was actually working, we'd probably get something that looked like this. That would be what would be sped up by an actual functioning, working parser. Cool. Okay. Oh, it's over. We still have some to go, unfortunately. So stay tuned. So we've successfully passed JSON. So before I proceed, does anyone have any kind of questions about what I've just kind of shown you? Like that, I'm just going to like go back to the JSON parser that we had before. Yeah, here we go. That's like the kind of core of it. Any questions about this? Bit gibberish, but hope everyone's kind of getting the gist. We're able to like directly translate this EBNF to like the main core parsing infrastructure. Kind of cool. Hey, okay, we're getting no answers. No questions, no questions. Let's proceed. I noticed that I got a dislike on this YouTube stream. That kind of sucks, man. Okay, let's go. So why? Like, why I spend all this time? So what I was trying to show you there was like the combinator pattern. And the interesting part of the combinator pattern is we kind of, like at least in the case of parser combinators, we have some type A, in that case it is parser, and we have a bunch of functions that construct primitive values of that parser, and then we have functions for transforming values of that type parser, and then we have combinators which combine parsers with other parsers. And you can kind of see the three kind of main types of the functions we looked at in the talk. You can see item, one of, unit. They're primitive. They don't take any parsers. They just spit out parsers. Transformers take parsers and produce new parsers. And then then combinators, they're taking two separate parsers, two or more parsers in some cases, and spitting out brand new parsers. Unfortunately, I've run out of room on the right-hand side of the screen, but you can kind of get the gist there. But I've already spoken to you about something like this before in this talk. And for a talk about testing, I didn't really spend that much time on testing. In fact, around the 23-minute mark, I spent like a solid 20 minutes talking about this thing called an arbitrary. Now, for those who don't remember what an arbitrary was, arbitraries, I showed you, they were ways of generating, data. So in this example, I created an arbitrary of user. And then on the right-hand side, you can kind of see the user objects that were getting created. As you can see, they had like really crazy emails that were valid. They had names that were like Latin sounding, kind of cool. And, they had, optional fields and different Boolean properties, that kind of stuff. Now, what is kind of interesting is I presented these arbitraries under different headings. And I know this is a bit blurry, but if you look at the headings I presented to you, they were these ones. There's primitive arbitraries, there's transforming, we can transform arbitraries, there's functions that transform arbitraries, and then there's arbitrary combinators. And so if we look back at, if we look back at the operators that we were just talking about with our parsers, I want everyone to stare at this for a second. I want everyone to really take it in. Look at the functions. Look at what they're taking. One takes a function and maps over it. Another one takes a parser and takes a parser of A and gives us a parser of a list of A. Another one parses a char. Bam. They're the same functions. See, char, like, okay, item passes a char, because JavaScript doesn't have a char, type, but so this char function gives us an arbitrary of string. Constant from, it takes a list of values and gives us one of those, it generates one of those values. One of, in this case, takes a char and passes one of those chars. Constant takes a value and generates that value. Unit takes a value and passes that value. Map takes a generated value t and converts it into a generated value of u. Map takes a passed value of a and turns it into a passed value of b. Plus, it's going to take an a, it's going to repeatedly pass a's, and it will yield an accumulated list of a's. Array is going to repeatedly generate t's and give us an array of t's. One of, it's going to take it's going to take a list of arbitrary of t's, and it's going to choose one of those t's, and it will generate that t. That's exactly what this almost alternative one is. It's not taking a list in this case, but it's taking one parser or another parser, and it's going to yield the result of one of them. Flat map takes a parser that takes a parser of A and a function that takes that A that gives a parser of B, and it will give us the result of that parser of B. It's exactly what that chain function does. It will take that, it takes an arbitrary of some sort of T. It will take a function that takes that T, gives an arbitrary view, it gives it an arbitrary view. This last one is a bit of a stretch. Chain L1 is kind of really useful for generating nested data structures, and Chain L1 parses nested data structures and using a kind of core parser type where those the things that we actually care about, and then using op, which is the thing that combines them together. In this one, in this kind of key value map, you have the core thing that we're trying to pass, and another arbitrary that will consume those two things and combine them. As you can see, it takes a key and then turns the arbitrary. Anyway, both Let and chain deal with nested data structures. So, we're noticing that these two separate concepts, parsing and data generation, almost have exactly the same API. Well, I wouldn't say exactly the same, but they support a lot of the same common operations. Their names are a little bit different, but the function type signatures kind of match up, in some cases one-to-one. Now, here's a really cool bit. If we actually go, this is the fast check library for TypeScript. If we actually go to the documentation and look up each of these functions, we'll notice that they're just listed under the combinator section, which I thought was kind of funny. But if we go back and compare these, well, why is there this kind of relationship between these kind of two APIs for what seemingly is completely different domains? And this is kind of my pet theory, is that they're kind of the same. They're kind of the same thing. A parser, as you can see, our X operation is just we're just going to call it combine, right? What we're going to do is we combine three parsers together. We combine a bunch of parsers. We can provide an input string, and what we get out is we get some sort of structured data, and we get the result stream out. Whereas with arbitraries, what we do is we cram in we combine a bunch of arbitraries together. We cram in an input seed, not an input string, and we get other structured data out, and we get a brand new fucking what's it called? Random seed that we're going to use in future computations. We're going to constantly do this over again. We take the old input stream. We take the old random seed. We get a new random seed, and we feed that random seed into the next arbitrary, and over again. Much the same way a parser takes an input stream, does something to that input stream, gets that input stream, that output stream, and feeds it into the next parser. So in some ways, they're kind of the same. They're kind of the same two sides of the same coin. It's kind of cool. But it also goes to show that this kind of combinator approach, we can kind of bend and contort to fit all different kind of domains. In this case, parsing and data generation, which seem to be completely opposite concepts, are in fact kind of the same and support the same API. So, any questions? Yeah, we'll leave it at that. Any questions? There's still a little bit left of the talk. Don't go just yet. Now we have some practical stuff because all of this has been theoretical so far. Cool. I'm going to say, why Scala? Yes. Okay, we're going to get to that in a second. So actually, another thing I want to raise is what we have is we have these this map function and this chain function, which is we have map and flat map, as you can see, have very much the same function signatures. There's some sort of concept that instantiates both of these data types, both arbitrary and parser, as a member of some interface. I'm not going to name what that interface is, or interfaces. I'm not going to name what those interfaces are. You should do Comp 3400 if you want to know what those are, because unfortunately, this isn't a talk about functional programming. Now, okay, first of all, don't use what I wrote in, don't use what I wrote in prod. Don't do it. Please, for the love of God. So why it's slow? We're allocating a bunch of allocating a bunch of anonymous functions all the time. We're doing a bunch of recursion. This is kind of ugh. Two, it doesn't do proper error reporting. As you could see, what happened was before my parser wasn't working, and I had absolutely no idea why it wasn't working. Just couldn't figure it out. Another thing is if you pass in some sort of string that isn't syntactically correct, your parser is just going to be nah, I couldn't pass that. And it's going to say error. It's not going to explain in any way why it failed to pass it. It's not going to explain what characters it kind of expected. Bunch of stuff like this. So another thing is it can't do backtracking. We can't, remember how we had to eliminate that left recursion in that kind of initial thing? That's because, well, when we consumed the entire string and we couldn't pass that last ABB, we couldn't say, actually, we want to go back. We only want to pass some of the stream. And then when we pass this last little bit at the end, don't consume all of it. We can't actually do that. And then finally, it can't handle left recursion natively. We actually have to rewrite some of our strings to get it to work. So because you shouldn't use what I wrote in prod, you can use these things in prod. Java Cup can do backtracking. There's actually a bunch of libraries that are really well written and they do exactly this kind of stuff. The important part is that these have almost very similar APIs with a bunch of extra bells and whistles. You don't really need to know under the hood. In fact, some of these use regexes under the hood because regexes are fast. And what's going to happen is you're going to write parser combinators and they're going to compile down a regexes. And so a bunch of stuff they do proper error reporting, they have backtracking, they have debug points, you have tracing so you can see what your parser is doing at any point in time. Really, really, really cool stuff. Now, another thing to note is Parsec. Parsec was the OG, the grandfather of all these separate parsing libraries. To the extent that I'm not even sure if it was the original implementation of the Parser Combinator paper, but to the extent that it is so popular that other there's other libraries that just use the Parsec name because in some ways Parser Combinators are synonymous with Parsec. And the really cool bit is they've copied the API. They've kind of copy pasted the API directly and you kind of can reuse the skill set that you've developed using parser combinators in one language with many different languages. In fact, you can reuse the skill set that you have developed using parsers in general for a lot of different domains that use parsers. So yeah, now if you want to, so this was like a really theoretical talk about, well, how do parsers work? How do we build them? What is their core implementation? What do they do? What are they justified? What is the relationship between regexes and grammars and NFAs and DFAs, that kind of stuff. Really like kind of theoretical. You can use these libraries to go forth and actually like parse some structured data if you want. If you really want to like, my personal recommendation is if you want to like figure out how parser combinators like can be used for practical purposes, I would recommend this article. This is like really practical demonstration. The guy who wrote this, super smart, really good writer, really clear. His libraries, I know they're in Scala, but they're very like inspired by Python libraries. He's re-implemented requests. He's re-implemented Bottle, which was the predecessor to Flask. Really kind of clear, reasonable writing in a library that's actually quite easy to use for a lot of purposes. So yeah, if you want to learn more about this, definitely read this article. And that is the last slide. Thank you so much. I have talked for far too long. Holy shit, an hour and a half. So yeah, that's about it. Thank you so much, everyone. If you have any questions, you can ping me on Slack, MB. Thank you for everyone who is not members of UKCS for tuning in. Thank you for everyone from UKCS who's tuned in. So yeah, cool. Oh yeah, any questions? Oh, yeah. Wait, oh shit, okay, I'm here, looking at myself on the stream. Yeah, does anyone have any questions? Yeah, okay, so I'm gonna like go through some of the questions asked. Okay, why Scala for this kind of work? I know the compiler course in my old uni before I transferred to UQs in Scala. Any alternatives? Why I used Scala is because it is syntactically similar to TypeScript and the Python typing module. Two, I've have 3 years of experience with it, and I wanted to use the laziness capabilities provided to me by Scala. If I were to not use Scala, I would have to do a bunch of little tricks to stop infinite Stack Overflows. You noticed a Stack Overflow that happened earlier on the talk that I had to like kind of stop the talk to kind of fix. That was because I fucked up using laziness. Yeah, you have to kind of be careful about how laziness works with these kind of things. So, and particularly with recursion. Yeah. Another thing is, if you really want to learn about this kind of stuff, do Comp 3400. This was covered in great depth by Tony Morris, who is a really, really, really skilled functional programmer. He does really fantastic Haskell courses that you can look up. The Data 61 course is really good. Yeah, cool. Yeah, Tony, Brian, and Fraser. Yeah, cool. If you have any questions, ping me on Slack. Sweet.
All right, cool. Thank you so much, Max, for that. That was awesome. Again, thank you everyone for watching. Remember, we have 2 other events this week. We've also got on Thursday, we have our Working Mouse talk about how to build software with quality and speed at 5 p.m. So make sure you come along to that. And Saturday night, we have a UQCS movie night where we're watching Catch Me If You Can. So definitely come along and hang and watch that. But other than that, thank you again for watching, everybody, and we'll hope to see you next time.